Okay, it's 12 o'clock and it's time to resume our webinar. So our next speaker will be Chair Cameron, and he will be talking about digitalization of UK aluminium anodization. Chair?
Yes, hello. All right, should I share screen here then?
What do you? Yeah.
Yes, I'll go ahead there. Okay, is that visible for everybody?
Yes, that's perfect. Excellent.
Okay, so as Alexei mentioned, I'll be talking about scope for digitalization in this sector. There's a bit of background to the project. It was funded by the DSM Network Plus to basically investigate what potential we have and what the pathway forward should be for digitalization in this sector. And it was carried out at the Centre for Intelligent Autonomous Manufacturing Systems at Queen's University Belfast. And during this project, we had industrial engagement with a variety of UK anodizers ranging from aerospace, kind of decorative anodization, architectural and automotive sectors. The scope of the work in general was to review the principles of anodization and see where we stand in the state of the art, investigate the type of work that British anodizers do and the challenges that they face, and then propose a digitalization template that can support that industry. So we'll go through a little bit briefly the fundamentals of anodization and the sort of generic procedure that people do, have a look at the field of commercial aluminium anodization in Britain, and then look at the challenges that are faced there, and then have a look at how digitalization can address some of those. So anodization is an electrochemical process. I will not go too much into the science here other than to say that we apply electricity to grow an oxide layer that's much thicker than naturally forms in the air. The interesting thing about most aluminium anodization processes is the electrolyte that the aluminium is in when this anodization is being performed actually dissolves the oxide layer as it's forming at the same time. So this has a couple of effects. One of the things that does is it reduces the efficiency, but what you do get is this very interesting porous layer going on top of a solid layer, and it has a lot of different properties, and this is what we're interested in most of the time. So we'll start by talking about the barrier layer, which is the simple solid layer that forms at the surface of the aluminium. So you have bare aluminium metal and then an oxide layer formed on top of that. And this is formed at the start of the anodization process, and it will remain at a constant thickness as you keep running the process. This is a well-established mature process, and there are kind of universal rules for how thick that layer will form based on the voltage you apply to the circuit. Now, the porous layer, though, is the interesting part that gives a lot of different properties to an anodized finish. So what it is a regular structure of hexagonal cells, and each of them have a pore that runs from the top of the cell down to that solid barrier layer of oxide. And when we speak about the porous layer in aluminium anodization, we talk about its morphology. So this is the width, the spacing, the depth, the shape of the pores. And these structures are affected by basically all of the process parameters, temperature, voltage, and also the alloy and any additives. So it's quite a complex interaction that creates this pore. As a very rough rule of thumb, higher voltage means bigger pores. There's a lot that goes into it. So it's a field that's been around for a long time, discovered in the 1800s. And a variety of work has been done scientifically around anodization. So in terms of the first principles modeling of this pore formation, this interesting layer, the exact mechanics are still actually under debate a little bit, but sort of the behavior of its formation and the expected properties of the structure are quite well characterized. And it could be possible to model the formation of this if you knew exactly the materials, exactly the conditions, exactly the process parameters. But there's no evidence of that level of sort of first principles mathematical modeling being applied in industry. It's not really used to formulate parameters there. Sort of a level up from that is data-driven techniques, where essentially what you do is take a controlled environment and undertake anodization in that and measure all the different variables that you're changing and derive a relationship to work out what thickness the layer will be, what the pores will be like. This has shown useful predictions in lab settings and very controlled settings. Quite good models have come out of that, but there are issues generalizing across different processes, different alloys, different additives, and in the practical terms of industry, different tank sizes, shapes, part geometries. So there's difficulties with data-driven estimation as well, which kind of leaves you with the last option you have in some respects for if you want to know what's happening is you can measure it. So if you wanted to measure this as the oxide is forming, you need equipment that can take measurements in that aqueous environment inside the electrolyte. And again, in lab environments, we've seen contact and non-contact methods that have worked to measure the pore or the oxide layer thickness, and in some cases, some of the properties as well. Of particular interest that I'd highlight is electrochemical impedance analysis, where essentially you inject a signal into the structure, and from that you can tell potentially an awful lot about both the microstructure and the thickness. Microstructure is interesting because generally if you want to find out about that pore morphology in detail, you must use a scanning electron microscope. And for obvious reasons, most anodization operators do not have a scanning electron microscope on the shop floor. So that's the basics of the process, or the fundamentals of the process out of the way, and I'd like to now take you through what anodization looks like as a procedure. And you may see on the slide here, there's 5 items, and only one of them is anodization. And that's because in a lot of industries would refer to their anodization line as a clean line. The process must be kept very, very tightly controlled. All contaminants must be controlled very carefully, and the pieces must be very, very clean as they move through the anodization line. So we'll start with the very first part, which is to note that anodization does put this surface coating on a metal, this protective oxide, but it does not change the roughness at a macroscopic level. So that means whatever texture you want on your final part, be it milled, brushed, or mirror polished, that needs to be in place before the part enters the anodization line. That has a few implications in terms of you have to handle the parts carefully and have good logistics around transportation. But the upshot is all parts must be brought to their final finish before anodization begins, and they have to be very, very thoroughly cleaned of any grease or other deposits from manufacture. After you have those relatively clean parts at their final finish, they go into jigs for anodization, and that's just a way to hold the part that makes an electrical contact to it. So as the parts are loaded in, they must have a good low resistance contact to this jig, and it's a process that can be very difficult to automate. The picture here is quite a simple jig, but if you're using different shapes of parts, different shapes of jigs, it is very resistant to economical automation. Once you have your parts loaded into jigs, again, we're going to clean again, because as I said, this is a clean line and there's a lot of cleaning processes. Usually several different series of rinses and cleans are done to the parts before they even start anodization. So assuming you manage to get all the machining oils and any other contaminants off, you will still have a natural oxide layer, which is just formed by the aluminium being exposed to air. Now, this isn't the oxide layer we want, though, for anodization. So that has to be etched off before the anodization process begins. And it's essential that parts are completely clean and completely bare metal before they enter the anodization tanks. So we have now bare metal parts, very, very clean, in their jigs, and they're put into an anodization tank, which is this electrical circuit. So at the start of this process, apply a voltage between the cathode and the anode, and the current is transferred via the electrolyte. And that voltage is applied in 2 stages. We have a ramp up stage and then a dwelling stage. And during the ramp up, that's when we get that solid barrier layer of oxide formed. The reason the voltage must be ramped is because at the start of the process, because you have bare metal in a conductive electrolyte, it's essentially a short circuit. So if you put the voltage too high, you will burn the metal essentially and cause problems. So the voltage is slowly increased, and as that oxide layer grows, which is non-conductive, the resistance of the circuit increases, and so you get a steady layer growth. After you have completed this ramping phase, you have grown your solid layer, and it's time to move on to growing that interesting porous layer. The porous layer is grown during the dwell phase, where the voltage is held at a steady state. And after a certain time lag, the current will also settle at a steady state. And then during this time, there's a balance between how quickly the oxide is being dissolved and how quickly it is growing from the metal. And obviously it's growing faster than it's being dissolved if the process is running correctly. So the longer you spend in this dwell phase, that makes for a thicker coating, and that's how you control the thickness of the final oxide coating. An interesting note about this is that it has a sort of a self-regulation built into it. So the rate of the anodization is based on current density or current per area of workpiece, not the absolute amount of current that is going into the job. And that just means pieces that have a large surface area will draw more current, pieces with a small surface area will draw less current, and that's generally why we'd use a voltage control for anodization processes. Once you have your porous layer grown and your oxide is finished, you'll take the part out of the tank. But at this stage, that oxide layer is vulnerable in some respects. It's described as open. So the pores will basically uptake anything around them very readily. And this is actually, it is desirable, but you need to do something about this. So if you want a plain oxide coating, you can just drop the parts into deionized water, and that'll hydrate it and seal the pores. And very, very commonly, it's put into a dye bath, and the dye will then, the molecules will go inside the pores and they will retain that color, and that's how you get a colored anodized part. And conversion coatings, which I'll talk about a little bit later, use the pores a slightly different way, but they still make use of the fact that the pores will uptake whatever they're exposed to. So that's a very, very high level sort of view of anodization and the different steps you need to go through. And as I say, I would like to underline the fact that the cleaning and the rinsing, if anything, I have underemphasized that it's a very, very important part of the process. So we'll look at a bit about the type of anodization that's done in the UK now and the type of things we use anodization for. So there's a lot of different applications for anodization, and this is due to the fact that you can have a very wide range of properties from that oxide finish. So you can have a hard film for excellent corrosion protection. You can have those softer films that are very, very good for glue, paint, and dyeing. And you can basically modulate the properties of your anodic film by changing your process additives, your process parameters, and the alloys that you're using. So it really means there's a wide range of applications for anodization. A few of the different sectors that use anodization: aerospace sometimes uses it as a final finish because they can get an extremely hard wearing finish from that, and commonly as well for those conversion coatings, which help to basically increase adherence of different glues for joining or paints for coating. Automotive and motorsport enjoy the properties of anodization because they can use lightweight aluminium parts and then put a very high abrasion resistance coating on it and also maintain very, very good geometric accuracy. Food and medical equipment, construction, power, oil and gas, again, generally enjoy the fact that you can have a corrosion resistant coating that's also quite cleanable. Architecture enjoys for cladding or other parts exposed to the elements, a way to put color into metal that's actually very long lasting in terms of, or in the face of rain and sunshine, and also corrosion resistant. And consumer goods is the one that we're probably all familiar with, and I guarantee pretty much everyone will have something cosmetically anodized in the room with them. And we've all seen carabiners on key rings. If you cast your mind back to when those iPod Nanos were very popular, all those different colors they came in, this is cosmetic colored anodization. So the different types of anodization that we'd see, these 5 different ones I'm going to talk about. We have type 1 chromic acid anodization, and this is the oldest established type, patented in 1923. This has a slightly different oxide structure, which is interesting. Instead of the regular porous structures, it actually kind of collapses on itself and forms almost like a plate armor when you look at it at a microscopic level. It's a very, very hard coating, and it's still used in the aerospace industry today. Type 2, technical or cosmetic anodization, is the type you're probably most familiar with. This is performed at ambient temperatures and using this sulfuric acid electrolyte, which is dissolving the oxide as it forms. The porous layer created by this type of process is actually ordered down to the nanoscale, and potentially, which did spur some research for a while and some interesting nanoscale properties that you can get from anodized coatings. But most commonly, this is used for dyed parts and cosmetic anodization, and the clarity of the finish is unmatched by any other type of anodization. We also have type 3 hard anodization, and in this, traditionally, chilled vats down to a cold temperature between sort of 0 and 10 degrees are used, and a very high current density. The implication of that is that you need the electrolyte to be cold, and you're putting a lot of energy into it and getting resistive heating, trying to raise that temperature. So the demands upon cooling infrastructure are quite extreme. In response to that, we see in the modern trade, some anodizers will use additives and the ambient temperature bath to achieve hard anodization. It's a little bit controversial in the industry, though, with some people would claim that that's not really hard anodization, while those undertaking the process would claim that you should just look at the final properties of the film. It's just something to highlight. And this, as the name suggests, is suitable for applications which need that hard coating with abrasion resistance. Conversion coatings I mentioned, so instead of sealing or dyeing the pores, different additives are presented to them, and they are adsorbed into the oxide. So they make a chemical bond, a very, very, very strong bond to the surface of that aluminium oxide. And then that chemical that has been bonded in acts as a primer for whatever your next coating is, hence the conversion. It helps you to move from one material to the next. And the last type is electrolytic anodization. It's called this. It's a little bit confusing because the process itself is electrochemical, but this is generally how this process is referred to in the industry. And this is for architectural applications which need that long-term color stability. And it's similar to cosmetic anodization, except instead of dye, we are embedding metal particles into the porous structure. So the analog process, which was pioneered in Japan, is currently operated in the UK by United Anodizers under license, uses cobalt metal, and that creates shades anywhere from light bronze to black, depending on how much metal that you deposit onto the film. So those are a few of the different types of anodization and an idea of the generic procedure. So we'll see now what sort of challenges there are in operating that and achieving good, consistent results. I'll take it through 4 of the most common defects you'd see on an anodized part. So the first one would be pitting. And this is not necessarily the fault of anodization, nor is it unique to anodization, but it's nevertheless a common problem with metal finishes. And it's usually caused by a contamination of some sort. It could be oils or acid or alkali attack, and can be galvanic corrosion sometimes. So this is a lot about design, logistics, transport, and managing, looking after the metal if you want to avoid this. There's not much you can do, but anodization will tend to make this underlying problem much more visible once it's been applied. Streaking is basically a slightly dull looking section, or basically a different looking section in the anodized finish, which should be uniform. And the problem with that is the metal hasn't responded the same way as the rest of the piece to the anodization process. So the film hasn't grown in the same way. And this arises because of maybe stresses in the metal or inclusions in the alloy, or any little impurities that have been sort of introduced or ground into the metal structure. And again, a lot of this, it can only really be prevented by carefully handling the material and being thoughtful with the manufacturing and bearing in mind the final finish that you want to put on the part. Burning is localized discoloration of the film, and this is actually something that would generally be caused by some problems in the anodization process. So what usually happens is that there's an overheating at a certain point in the film, and because that anodic oxide is under attack by the electrolyte because it's being dissolved, where that overheating happens, the dissolution happens faster too. So it basically burns its way straight through the oxide and you're left with a rough part. That can be mitigated by using appropriate voltage profiles and making sure that the electrolyte in the tank is being agitated to sort of move around any hotspots and prevent that. And the last defect I'll talk about is chalking. And chalking is a white sort of powdery deposit that would appear on the surface. And that's basically the loss of that geometric pore structure. It collapses and it forms this powder instead. And that can happen when films are too soft, which could be not enough current density. And you may notice then we can have burning if the current density is too high, chalking if the current density is too low. So it's clear that if you're undertaking a process like this, there is some envelope that you must stay within to get a proper result. And chalking can also happen if you have a very long dwell time because the acid has been attacking that oxide the whole time, weakening it. So the defects are obviously if you're running the process, the part loading and unloading. When we think about that, it's a big important part because of the need for this to be an electrical circuit. So the jigs themselves, titanium is the favored material for them, and the investment in them can be enormous. It can be very, very expensive. However, that aside, there are some processes that can't be run with a dissimilar metal. So you have to use an aluminium jig. And when you're using these aluminium jigs, every time after you use it, you need to strip it back again before it can be reused. Regardless of the type of material of the jig, one of the issues is you'll not often know if the electrical contact was good or not until right at the end of the process when you actually see the finished part and did it anodize correctly or not. So I mentioned that there's a lot of different stages to anodization, a lot of different tanks it has to go through basically for cleaning and etching, and the parts are loaded at the start of this, and then they go through all these tanks. They're being lifted, transported, dumped, the tanks are being agitated, and throughout all of that, the parts have to remain securely attached to the jigs, and not just that, it has to be a good quality electrical connection that those parts have. And the contemporary work we see these days, and we heard earlier about some of the issues with basically the easy work being offshored and most surface manufacturing in the UK being technical and difficult. This leads to manual loading into custom jigs for a wide range of geometries, which is difficult to automate and takes more time. In some cases, if the run numbers are large enough, it's better to just quickly load reasonably well and accept a higher failure rate in a batch. But one of the issues too with the manual loading of jigs is you're introducing a vector for contamination again. And every single anodization company I talked to told me at least one anecdote about finding a fingerprint in the finish. And when I talk about a clean line, that's really what I mean. It's enough for you to just touch it with your fingertip, and that will destroy or it will compromise the anodized finish. So one of the critical things that we want when anodizing a part is a film of the correct thickness. And the unfortunate thing about this is that thickness is affected by the temperature of the electrolyte, the pH of the electrolyte, any additives, the voltage you're using, the type of alloy you're using. It's not a simple calculation to work out how long that should be. So the general procedure here is a test piece would be included within the batch, and that test piece is removed earlier than we'd expect the anodization process to be finished, and then we measure the thickness of the film that has formed so far. From that, you can calculate the expected growth rate, assume it's the same for all the parts, and then calculate when you should stop the process. Few issues with the assumptions there that you're assuming it's the process is the same on all the different parts and all the different types of parts, but this is how it's generally done, and it's reasonably reliable. There are cases that when you remove that test piece, the anodization is already at the correct thickness, in which case you stop the process immediately. But it's also not uncommon that you remove that piece and you see that the film is too thick already for a geometrically accurate part that may be beyond tolerance now. So you either end up discarding the whole batch or you strip and re-anodize it if that is feasible for the part. And the reason that this can be an issue is an operator may be overseeing multiple tanks running different type of parts at the same time, and it can be hard for them to get these test pieces removed, measured, the dwell times calculated properly, and make sure everything happens on time. And in general, when we think about inspection and testing, I mentioned that chain of processes, and each is reliant upon the last. And generally speaking, each process is not able to mitigate or compensate for any failures, defects, or contamination introduced, so issues accumulate. So in the ideal world, we'd measure first that each process was correct and done well before moving on to the next. But that's not really practical because the time that takes to do this manual inspection would reduce the throughput of your line an awful lot. And even if you did want to take that time, there are issues that just cannot be spotted, like those micro stresses. You can't see them through inspection. The anodization shows them. So the defects become apparent after the process is done, which, if you have relatively fast inspection, isn't an issue. But for instance, corrosion testing in a salt spray chamber or other longer tests or off-site tests, there can be quite a large time lag between when the anodization production was done and when the test results came back, which can result in a lot of spoilage or rework if it turns out that the line has been producing bad batches for several days. And the last thing I'd like to talk about in terms of the challenges are process development. So we can think about these procedures and these allowable envelopes a bit like a recipe and a chef cooking something. So you would have a cookbook that has, ingredients and cooking times, but if you actually want to make that dish, there's a lot of skill and knowledge that's not included in the recipe. And this is one of the big ways that anodization operators add the value to their offering. So this is because they have the experience and knowledge to develop these exact procedures and know the different parameter envelopes and know how they can make adjustments to make jobs turn out well. And developing those procedures, even with that experience, can take from weeks to months. You have to take into account pretty much every aspect of the process to come up with something that works. That really puts a lot of inertia on how things are run. So anodizers do not want to change the process unless there's a very good justification. Any time spent doing this development is time not spent in production. And unless they're lucky enough to have a pilot line, it's very disruptive. And also any upfront costs on new equipment or chemicals can't even start to be recovered until the process has been developed. So bearing in mind that sort of the outlook of the sector, the type of applications we've got, the challenges and procedure, we'll see how digitalization can interface with that sector and how it might be able to support it and what sort of barriers we might face. So this is a kind of a digitalization architecture as applied to anodization. I'm not going to go through that diagram in a lot of detail. There is an accompanying report that this presentation is based off, so I encourage you to read it if you're interested. But we're taking a relatively standard, as far as these things can be described as standard, digitalization journey, where we want to network the processes together, embed sensors where we don't have them, and then combine that to get real-time visibility into what's going on the production line. All that knowledge and expertise should be integrated into a knowledge base, which can be then consulted and used to inform what's happening on the production line. And the final last stage of that would be doing things like leveraging computational intelligence and statistics to improve insights and hopefully support the operators and designers of the process. And it is a very personal journey for each company. I've split this into 3 phases, where we consider sensorization at first, integration into systems, and then that intelligence, that higher level. I think it's important when we consider digitalization that you should get some tangible and standalone benefits at each stage, rather than expecting companies to complete the entire journey and then get the benefits at the end. There's also a few technologies I've highlighted that I think are from the review of the moment now and could help in this process. So an in situ electrolyte sensor, basically to monitor the tank chemical conditions, an in situ oxide sensor, which again is feasibly buildable and has been proven in the lab, and auto dosing systems, which do exist but tend to be very expensive. However, due to advancements in microcontrollers and IoT, the costs of these things certainly can be lower now. Again, optional upgrades, but they will really magnify the value of going along that digitalization journey. The first phase one, sensorization, and again, I'll briefly discuss this diagram. The overall goal of this is to say we have some physical conditions in the tank and the process, and we want those physical conditions aggregated into a real-time data stream. And that's all this process is in service of. So where you have control panels that you can interface to, you interface to those control panels. Where you have maybe older legacy equipment that doesn't have digital interface, you can sniff signals off PLCs. Where you don't have sensors, you can install new sensors. And if you have wired infrastructure, you can use the existing wired infrastructure, and there's a whole host of different wireless sensor network technologies you can also embed if you would rather not run wires. But in the modern sort of landscape of digitalization, this doesn't present a problem anymore. Digital interfaces are very cost effective these days. They don't cost an awful lot. Same goes for nodes and transport. So the idea is, according to what is available in the factory and what isn't, you can either interface using external new sensors or take what's already there and aggregate this data into a stream. So that stream is your first tangible benefit. Now, it is quite a raw stream from that point of view, but you do have then an insight, a real-time insight into your process flowing through, which could be simply shown on a control panel, but more importantly, should be prioritized to be recording that data, because the further you go down the path, those data sets are very useful to help characterize and understand your process. Once you have your data stream, you can move on to integration. And in practice, you can do these in parallel to a degree as well. So we look at the data pre-processing. We've got that raw sensor stream coming in, and there are some additional metrics and calculations you can sometimes derive from this by combining sensor readings with each other or by applying models to them, like estimating the oxide thickness, for instance, if you don't have a sensor. And that basically changes your raw data stream into some useful process information. And you move on to then a data analytics layer. And this is where you want to start connecting knowledge and records from other different sources, like ERP and MRP programs, to take your aggregate information about where your job came from, the trajectory of how it's gone through other processes, maybe previous customer information, deadlines, and so on. This is all combined then with the information from the line. And overall, it's built up into not just raw sensor readings, you get states of the job. So you get the state processing at the moment, finished in 30 minutes on time for delivery, and you can start to get this understanding of production, a more semantic understanding of production instead of just a stream of data. But that understanding is still kind of trapped within databases and within computers. So the last layer, but a vital layer, is of course the presentation layer. And this is where operators and supervisors actually interface with the system. And it can be simple things like dashboards and alerts. It's very much dependent on working practices, and in this sector especially so because of how strictly recipes are followed. But the good news there is there are tools these days for companies to take stewardship of the visualizations they need to see and how they want to see them. So you can use tools like Node-RED or Microsoft Power BI to build the reports and visualizations that are useful to you. And at that stage, you've got really a nice semantic understanding of the process. There's less poring over graphs and looking at things, and more being able to see alerts when there's problems and green lights when things are well. The next stage after that is to try and start really leveraging intelligence and deeper knowledge and expertise. So there's a few different parts to this. There's a private knowledge base, there's the idea of cloud services, and then really looking to the future, there would be sort of third-party web applications. Starting with the private knowledge base, I mentioned that your sensor records, that data stream off the line, should be archived right from the start, because these are valuable records. It's useful data. It's what you build your models from, and they'll build up naturally over time. And as I say, they do have value. The additional notes and tribal knowledge from the operators of the anodization who know how to develop these procedures, who know the different mitigations they can make, and the red flags to look out for, should also be integrated into this private knowledge base. And this is, as I mentioned earlier, one of the big value adds that any given anodizer will bring. So this is very much commercially sensitive information, so it should be kept safe, and I would recommend self-hosting for something like that. You can move then on to cloud services like AWS or Azure. And here, this can, if you want to make some heavier computations, it can give you scalable computational infrastructure. You could store, for instance, public anodization procedures and standards, any larger pieces of data that aren't sensitive. It can be deployed in the cloud, reducing the burden on local IT. And it also sets you up for the link to, and this is, as I say, looking forward to the future, third-party web applications. We can imagine if the digitalization movement gathers up momentum, there are challenges common across the sector, and indeed there's sector cutting challenges as well. And the expertise required to solve some of these problems is certainly not in the business of an anodizer or a manufacturer. So a machine learning expert is not going to be on staff at an anodizer, but if there is a route for them to sort of deploy models and to work with anodizers and potentially come up with a generalized solution, then there will be an incentive for third parties to come use these heavyweight statistics and heavyweight computational learning to help boost the intelligence that anodizers can leverage. So I think it's a nice picture. A lot of it is certainly practical, but as always, there are barriers. And the first barrier will always come across as interoperability. And it's notoriously difficult. There's no way around that. In most cases, companies will be gluing together different siloed data and proprietary interfaces just using human labor and hard work, maybe carrying a USB from one computer to another or copying a number from one control panel to the next. The only mitigation really here is to use open source frameworks, keep great documentation about how the system works together, and build in the flexibility and expect that it's going to need to evolve and change as the standards do. A big issue in this, because of where the value lies in running anodization, is the security of trade knowledge. Operators may be uncomfortable digitizing their own expertise, and a company risks disclosing their knowledge and wisdom if they integrate with third-party services. And a question which may arise in the future is if a third party comes along and says, we'll give you a machine learning model to help predict the quality of your anodization, and they train it using one company's records, what if they then publish that model and to the benefit of a competitor? Now the data, technically, they didn't publish, but the model came from one company's data and is used to benefit another. So that, I think, is something we'll see as a debate, but there's certainly no easy solution to that immediately. One of the issues too here is that oxide sensor is not readily available to industry. It's proven in lab settings where we can measure anodic thickness online, but it hasn't been developed commercially. I would say that particular measurement, while it could be estimated using other data, it would make a huge difference to the digitalization process and anodization. So I would highlight that as a priority. The difficulty of automation, I raise this and say that because the type of work that's done is very resistant to automation. So I don't think it's really worth exploring from that point of view at this stage. But just to underscore that the digitalization benefits here are informative in nature. Could be flagging difficult jobs, monitoring the state of different jobs, and better visibility into the process. And just a reminder that digitalization is not automation. They often happen together, but they're not the same thing, and digitalization has benefits outside of that. And the last, and I really think the biggest barrier here, is the established working practices. There's a good reason for them. You saw the complexity of the process. So one way to do it is one way to get around that is to be very, very strict of how it's done. And those practices have been developed and refined over a long, long time. Any mitigations or tweaks have also been learned and battle tested. So any digitalization system entering that environment has to demonstrate value right from the start and will also need to build trust. It cannot force a change in habits. It must sort of support people to do their jobs. So a few suggested specific applications that I would say if you have the digitalization framework like this in place that open up. So one would be that film thickness monitoring, and simply instead of using a test piece, you would get an alert or a readout that tells you the film thickness, and that alone makes a huge difference. The process development support. I mentioned that there is a cost. I think it was mentioned earlier that chroming won't be allowed anymore, except in some sectors. So there will be a general move away from harmful substances and chemicals, and that means developing new recipes. So a sensorized tank that's both monitoring and controlling the parameters of anodization more closely could really accelerate the development of those new processes. Parts traceability, again, this isn't a unique benefit to anodization of digitalization, but it's particularly helpful here because a lot of those defects we saw aren't necessarily the fault of anodization. It's the history of where the part was and the manufacturing process that happened to it. With a framework like this, you'll be able to track that sort of effortlessly. And one thing could be done is to flag difficult jobs for extra cleaning or for extra attention. The auto adjustment of process parameters is another thing. So we talked about these envelopes of allowable conditions. If the system itself is able to have a model of the interaction of these parameters, it may be possible to open up that envelope for the chemicals, for instance, extending their lifetime, or to better compensate for ambient temperature anodization where the tank's at different temperatures, and in general improve resilience to disruptions. With the digital framework in place, you can also look at relatively easily integrating things like computer vision systems, which can quickly inspect parts a lot better than a human can do, especially if it's well defined the problems they're looking for, and even look at more novel technologies like hyperspectral imaging that could potentially spot things that can't be found by eye. And the last one, this idea of you load the jig, hope for the best, and then see how the anodization turned out at the end. With repeat jobs or an expectation of how the voltage and current relate to one another for a properly jigged job, it may be possible to even just automatically flag an out of spec electrical response from a job that hasn't been jigged correctly or has a poor connection. And so before you anodize and before you get that spoilage, it would be possible to just have an alarm go off and say, check that jig. So to summarize, a few things that I think would help push along in the research and innovation, this movement would be just work towards a generalized model that can take into different accounts contaminants, additives, alloys, and have a better expectation of anodic film growth, because it is something that is lacking in the literature. Design of experiments for these parameter envelopes. So we have a desired result and with a tolerance, and then there's a lot of different aspects of the process which will have a nominal value and then a maximum and a minimum, like maximum voltage and current densities. So finding the link between these two things is basically done through finding when pieces start to fail. A methodology to quickly find those limits based on specifications or even calculate them would again save a lot of time in process development. That in situ sensor I've mentioned would be a revolutionary thing. It would very much help with this labor of checking test pieces all the time and managing the process. And finally, the tank monitoring and auto dosing. Given the advancements and reductions in cost and technologies, it should It'd be feasible to have a lot cheaper tank auto dosing systems, and with a digitalization framework in place, there's a lot more benefit to an auto dosing and tank monitoring system than there is when you have a highly manual line. So in conclusion, just like to note that the UK anodizers are generally competing on that high quality, short run, difficult work, and those jobs are resistant to automation. The working practices, they're disciplined, they've been developed over a lot of experience and time. And really the challenges are defects are difficult to catch before they're already done. The process itself is run as a recipe, which is understandable, and there's a good reason for that, but that results in disruptions being difficult to mitigate. It's very time consuming to come up with new recipes as well and to refine them. And the management of the tanks themselves is labor intensive because you're following that recipe so closely, you're controlling the conditions and using those test pieces to monitor film growth. If applying digitalization to that, we could see operations enhanced through easier process monitoring and management, better leverage of the knowledge that's inherent in the company, and assistance in parameter development and tuning. But overall, the whole approach must be one of decision making and operator support, because there's a lot of understandable inertia and skill that goes into running anodization now. So the idea is to help magnify that skill, not take it away. So thanks very much for your attention. The full report that these slides are sourced from is available through the DSM network and also at the link shown on the screen. If you have any questions,